object is often important. If Sue is taller than John, it's true. If you reverse it, that would be false. If you say that, okay, John is taller than Sue, that would be false in that case. So the order is important. Now, formally, what is a relation? So this is what we concluded in the previous lecture. Therein we said a relation is a statement about ordered pairs xy that are in the same type of collection, I mean A cross A. The statement is either true or false for each pair xy. Either x is related to y or x is not related to y. Okay. So relation is the property that we define. So consider, now we're going to say this is a relation, okay, and if we define this relation on this set, then what are the ordered pairs we're going to get? Okay, so here 5 and 3 are related. 5 is related with 3 because 5 is greater than 3. Is that right? Okay. Then 6 is greater than 3. 8 is also greater than 3. Do you agree with me? Okay. What are the numbers we got? We got 6 greater than 5. That's another relation. And 8 greater than 5. Yeah. And then we have 8 greater than 6. Is that all collection we have? Or are there any other possibilities?
8 greater than 3.
8 greater than 3, which we have. So first I fix 3 and look at other numbers, 5, 6, 8. So 5 greater than 3, 6 greater than 3, 8 greater than 3. Then I move on to 5. I fix 5. So 6 is greater than 5, 8 is greater than 5. Then I fix 6, and there is only one possibility that 8 is greater than 6. Okay. So this is the example of relations. Do you see here that I have got the collection of subsets there? I mean, not collection of subsets. It's a set where I have put together objects which are under this relation. Okay, and that relation is greater than, if I say that R is defined on A cross A. Do you see that? First element is from A and the second element is also from A. So this relation is an operation, I should put a star, on A cross A. Okay. So for xy, x is greater than y or x is not greater than y. So is greater than is either true or false for this order here. So is greater than is a relation. Okay, and we categorize that relation as well. So alternative way of defining a relation. So for some relations, if we don't have a simple verbal description, the relation can be defined by just writing down the set of all pairs. The set is denoted by R for relations. And for example, is greater than on the set A can be defined by, so exactly the example I gave on the previous slide. And so you put all those ordered pairs together to define the relation. If somebody looks at ordered pair, all the ordered pairs, they can see clearly that under what properties do we have collected them together. We can see first element is always greater than the second element in that pair form. So this is always greater than that, that's always greater than that, that's always greater than that, and that, so on. So that's a relation. Greater than is a relation. So if x is related to y, for example, 5 is related with 3, and 3 is not related with 5. 3 is not greater than 5, so I will put just cross on R to indicate that 3 is not related with 5. 5 is related with 3, so that means 5 is greater than 3, 3 is not greater than 5. Now, let's look at the graphical representation of these numbers. How are we going to define? What numbers we had? We had 3. Thank you. Okay. Now, these are the numbers I got. And I know 6 is greater than 3. Like this. Okay, so 6 is, so this symbol means greater. So 3 is less than 6 in other words. And similarly, 8 is greater than 6. 8 is also greater than 5. 5 is greater than 3. Efficient. Okay. Are there any other combinations? 8 and 3. 8 and 3. So that would be like this. And then 5 and 6. That would be yeah. So this is a graphical way of representing. These are the nodes, and these are the edges. If at some stage you study graph theory subject here, you will come across these kind of diagrams. Okay, this is the graphical way of representing these relations. We can also write this in matrix form. So let me try to write that in matrix form. 3, 5, 6, 8, 3, 5, 6, 8. So 3 is greater than 3. Is that right? No. 3 is greater than 5. Wrong. 3 greater than 6. Wrong. 5 greater than 3. True. 5 greater than 5. False. 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 6 greater than 3 is true. 6 greater than 5 is true. 6 can't be greater than 6. So this is true, 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 false. Okay. So there you can see that this is called matrix representation of these relations. Any questions so far? Pretty simple, I assume. Alright, so let me skip whatever we have written. I've drawn 2 graphical representation just to identify that. Exactly the same. If you understand that, then I don't have to repeat it. Here you can simply say 5 is greater than 3, so that's why that happens. Matrix representation of relations. So exactly the same way. You have 3, 5, 6, 8, 3, 5, 6, 8. 3 to 3 is false. 3 cannot be greater than 3. 3 is not greater than 5. 3 is not greater than 6. 3 is not greater than 8. So that's why all of them are false. The first item, then you have, after that, when you look at this way, you get that lower triangular matrix. Yeah. Yeah. This kind of representation is called matrix representation. Make sense? Right. Now the main thing that we are doing now is to look at the properties of relations. That's more important. It's not doing anything. My iPad is slow. Okay. Now we want to look at properties of relations and what kind of properties we can look at. Let me see if it is working now. Okay. Right. Okay. Yeah. Properties of relations. Let's look at here are 5 important properties that a relation R and a set A may or may not possess. So we're going to look into 5 properties. We have to be very careful with them. Sometimes they are sort of confusing. I don't think you will be confused with that. Properties. R is reflexive. A relation is reflexive if it is related to itself for every element that you pick. 3 is greater than equals to 3. If I have a greater than or equal property, greater than or equal, then this is true, right? So if I have this relation R, then 3 is related with 3, right? Or if you pick any x, that's not my x, right? If you pick x, it would be related with x for any x, right? If you choose this as your relation, is greater than or equals to, then this is always reflexive. So this property, if a relation can operate on the element itself, then it's called reflexive. If it's called irreflexive if there are no elements x for which that can hold. For example, x greater than x is wrong. 3 is greater than 3 is wrong, of course. It's always false. A number cannot be greater than itself. If I say greater than or equals to, then it's true, always. But if I say x is greater than x, just greater than, this is the greater than, then it is not true for any x that you pick. Do you agree? Okay. For example, Sue is taller than Sue. Oh, absurd, can't be right? So that's irreflexive. Symmetric. If x is related to y, that implies y is related to x. Okay. Can you give me some kind of a relation here that would imply this for any xy that you pick? If x is related to y, we want to look at some kind of a relation that would also imply y is related to x.
It is January in January.
It is January in January. What's the relation? So you mean having the same birthday, for example. If x has the same birthday as y, that means y has the same birthday as x. Okay? If x is born on 12th January, x is related to y if y is also born on 12th January, right? Let's say born on 12th January. Yeah? Born on 12th January. Let's say this is my relation. Then, if x is related to y means x is born on 12th January as well as y is born on 12th January. This also means then y is related to x. Because if x is born on 12th January as y, yeah, that means conversely also true. Put it this way. If x is a sibling of y, that means y is also a sibling of x. Yeah? So that is this property is called symmetric property. Now these things are very important. When we say for all x, no elements, for all x, y, so these are carefully to be looked at. Anti-symmetric, if x is related to y and y is related to x, imply x is equal to y for all x, y in A. We are going to go through these examples one by one soon, all of these properties, but first I want to just see that whether you can come up with some examples or not. So R is antisymmetric if X is related to Y and Y is related to X, but they are equal or not equal. Let's see. If I say is a subset of, let's say, is a subset of. If A is a subset of B, that means A is related with B, and B is a subset of A, that means B is related with A. This means A is same as B. If I say a set is a subset of another set, and that another set is also a subset of the original set, that can only happen if both the sets are the same. Okay. Right. So in that case, this is equal. Can you give me an example where X is related to Y and Y is related to X, but they are not equal?
Symmetric?
No, I'm saying not antisymmetric.
Oh, it's not even symmetric. What is
Yeah.
symmetric?
Here we have for all. When we saying equal, here we have only property that X related to Y implies Y related to X. Here we're saying whenever that happens, both of them, they have to be equal. Here we are not claiming that. There's a difference.
So your example of X being similar to Y, and Y is similar to X, but X isn't Y.
Yeah. X is sibling of Y. So is a sibling of, is a relation. So X is a sibling of Y, so Y is a sibling of X, but they are not equal, they are not the same. So that's not antisymmetric. In the previous case, but that property is symmetric. Yeah. Anyway, we have lots of more examples to go through. I will go one by one and discuss each of them at length. A property is transitive if X is related to Y and Y is related to Z, implies X is related to Z. Okay? So that means X to Y, Y to Z, this means X to Z directly. So you can skip Y in some sense. So that's called transitive property. If I'm related to someone and that someone is related to another one, that means indirectly I'm related to that person. So there are lots of examples you can construct. I won't go in that at this time for this one. I will go in later. Let's look at some examples now, one by one at a time for each property. Let's look at reflexive property first. What is reflexive? A relation R on a set A is reflexive if X is related to X for any X that you choose. Examples. Consider the relation is less than or equal to on the set of real numbers. Since the statement X is less than or equals to X is true for any number that you choose, that means this relation is less than or equal to is a reflexive relation. Do you agree with that? Okay. Now look at a relation which is not reflexive. Is less than, for example. So any number is not less than itself, so that means it's true for every number that you choose. So hence what you got not reflexive property. Yeah. Now here the distinction that you have to keep in mind, we are talking about for all. If X is related to X, and that property holds for all. Okay. Then when we move on to irreflexive property, We are saying no elements. They are not opposite of each other. Most often it happens if you have a property which is not reflexive, then that is irreflexive. But it is possible that none of them are true. Both of them are not true. So here talking about no elements, there we're talking for all. There is a possibility that for some of them it is true and not true for all. Okay? Right. Now, let's look at some examples of irreflexive. Is taller than, for example, is taller than. You cannot be taller than yourself. Okay? So that will never happen. So that's irreflexive. Another example, has the same year of birth as. Okay? So on the set of all people. What we're going to have there? Whether it is irreflexive or not irreflexive?
No.
Not irreflexive. Yes, because, I have the same year of birth as I have. Okay. So, here the statement X has the same year of birth as X is definitely true for someone, so the relation is not irreflexive. Anyway, as I said, this would get something when you look at all these properties one by one. If you have done one question just by yourself, you will think that that's extremely easy, but if you get confused at some stage, then it will become very confusing. Let's look at symmetric property. A relation R in a set A is symmetric if X is related to Y, implies Y is related to X for all X, Y in A. If you have one way, it's also reversed as well. What that means is a brother or sister of on a set of all people. So you have set of all people. So you have X. If X is a brother or sister of Y, that means Y is a brother or sister of X, right? Yeah, symmetric. Okay. And on the same note, this is not anti-symmetric. Because X is related to Y, Y is related to X, but X is not equal to Y, may not be equal to Y. So X and Y could be a boy or a girl, so you can't put them equal. Anyway, so for any people X or Y, if X is a brother or sister of Y, it must be true that Y is a brother or sister of X, so the relation is symmetric. Consider the relation is a brother of on the set of all people. If X is a brother of Y, that does not imply that Y is a brother of X. Do you agree? Y could be sister, right? So X is a brother of the sister, and then not conversely. So this relation is not symmetric. Do you agree with that? So we're looking at 5 relations and we're looking at each of them separately. Now look at antisymmetric. Antisymmetric is a relation R on a set A is antisymmetric if X is related to Y and Y related to X, imply X and Y are the same for any XY that you choose. Can you give me an example? An example where this would hold, an example where this would not hold. We've done the example actually at start. I did the example. So you just have to think. Okay, example please. Anyone? X related to y and y related to x implies x and y are the same.
The age of twins.
Okay. The age of 20.
No, twins like siblings. Stuff like that.
Hang on, I don't get it.
So
Twins.
Twin siblings, yeah. The age of
Oh,
one.
so you're saying that the set of all twins.
Oh no, there's like two twins.
Oh, your set has only two elements in it.
Yeah.
So they are not the same. Oh, their age is the same. you mean?
Yeah.
Ah,
Yeah,
I
yeah,
see.
yeah.
Okay, yeah. Good. Good. But this is a very trivial example. I gave an example of subset, but good one, satisfy the requirement, it's fine. Consider the relation is a subset of, okay? On a power set, for any sets x and y, if x is a subset of y, so in symbols you write x subset of y, and you write y subset of x, that can only happen when x and y are the same. If I'm saying that x is a subset of y and y is, okay, in other words, x is contained in y and y is also contained in x, that can only happen when both of them are the same. Otherwise, not possible. Okay. So that's an example of anti-symmetric. Now we look at the not anti-symmetric example. Consider the relation has the same number of pages as on the set of all books. Okay. Now there you can see set of all books. X is a book which has, let's say, 300 pages. Y is a book which, let's say, has 300 pages. So it has the same number of pages. So X is related to Y. Okay? Y is also related to X because Y also has same number of pages as X. But X is not equals to Y. Okay? Because they are different books. Of course. It's true for all. Whatever two books you choose, they are not the same. So this is not anti-symmetric. Right. And what we are left with now? Transitive. In the tutorial, we will practice lots of very similar kind of examples. You would have the relations in front of you. You have to verify everything. Yeah? So pretty much logic. A relation R on a set A is transitive if X is related to Y and Y is related to Z, imply X is related to Z. Okay, so basically you just skip the middleman for any X, Y, Z in I. Is less than or equals to, that's a relation. So 3 is related to 5. 3 is less than or equals to 5, right? Let's say 4. 4 is related to 6 because 4 is less than or equals to 6. You agree? This means 3 is less than or equals to 6. So this 3 and that 6, so you can skip that. That is transitivity. Transit. You are skipping something. Middle part. Yeah, you don't need that. If X is related to Y, Y related to Z, that means X is related to Z. So in general, if you have any number X, Y, Z, if X is less than or equals to Y, Y less than or equals to Z, that means X is less than or equals to Z. Now, this is the transitive property. Can you give me an example where something is not transitive? X is the father of Y, Y is the father of Z, that doesn't mean X is the father of Z. X is actually a grandfather of Z. Right? So that's not transitive. Any other example? It's a very good example. Any other example that you can give me?
X is another Y and Y is another Z.
Yeah, technically true. Example. Okay, let's put that in a different characteristic, yeah? Some other property. Do you know Pythagoras theorem? Yeah? Okay. You know Pythagoras theorem. Can you construct an example? Transitive example. You can. Don't shake your head. You can. You just have to think. If X is 100 kilometers away from Y, Y is 100 kilometers away from Z, does that mean X is 100 kilometers away from Z? Yes, so not particularly, yes. So that is not transitive. You are basically saying so this is, let's say, 100. X is related with Y. That is let's say 100. So X is related with Y. Y is related with Z, but X is may not be related with Z. That might be smaller distance. You go 100 kilometers south, then you go 100 kilometers east, then the distance from here to east, that place may not be 100, it might be less than that. Okay. So here I'm saying more than 100 km. It's possible you will be going less than that. Or similarly, at most distance. You can construct many of these kind of examples. Right. I have an example here is the father of. I had forgotten that. Anyway, another example. Now we are looking at a general example and we're going to see how many properties it satisfies. Determine whether the relation R is at least 200 kilometers from on the set of paintings in Australian art galleries is reflexive, irreflexive, symmetric, antisymmetric, or transitive. So the property that we're looking at is, the relation that we're looking at is at least 200 kilometers from. So, number one, we look at reflexive. If X is related with X, is that true for all X that you choose from A? What is A here? The set of paintings in Australian art galleries. Why not?
Because it's not 200 kilometers from the south.
Yes. Yeah, if an art gallery is in Bendigo, yeah, then a painting in Bendigo cannot be 200 kilometers away from itself. Yeah? A painting from itself cannot be 200 kilometers away, so it is not reflexive. Okay? Then the next property was there is no element in the set which is related to itself. Is there any element which is related to itself? This XRX is for all X, for all paintings. Next property is irreflexive. That is, there is no element. So, transitioning from for all to none. Now, is there any X related to X? No element. Yeah, so it is irreflexive. There is no such element which is related to itself. So the property is irreflexive. Yeah. Next, symmetric. Symmetric property is if X is related to Y, implies y is related to x for all xy in the set. Is it true? If x is 200 kilometers away from y, is it true that y is 200 kilometers away from x? Absolutely. Symmetric. Yeah. Next property. If x are y and y are x implies x is equals to y. If x is 200 kilometers away from y and y is 200 kilometers away from x, does that mean they are the same? Of course not. Yeah, of course not. Two paintings in different locations. They are not the same. And the final property. If x is related with y and y is related with z, does this mean x is related with z? If x is 200 kilometers away from y and y is 200 kilometers away from z, does that mean x is 200 kilometers away from z? Surely not. Not necessarily. If x and z are here at the same location and y is some other location, x is away from y by 200 kilometers at least, y is away from z by 200 kilometers, but it is possible x and z are at the same place. Yeah? So that's not transitive. So we have irreflexive, and then we have symmetric, and then we had antisymmetric. Yeah? Not antisymmetric, sorry. Two different paintings, yes. And not transitive as well. So only two relations were satisfied. So there was irreflexive and there was symmetric. This was not antisymmetric, not transitive, not reflexive. So only two of the properties satisfied for this relation. Yeah. So R is irreflexive and symmetric, but is not reflexive, antisymmetric, or transitive. A final example. Determine whether the relation R has the same artist as on the set of paintings in Australian art galleries. So you want to look at whether now for X is related with X, of course, reflexive. Any X that you choose, a painting is has the same artist as, okay. Of course, one painting is drawn by an artist, the same painting, of course, the way it is related with X is obvious. Then the next one, there is no such X, so definitely it's not irreflexive. Symmetric. If X is related with Y, implies Y is related with X for all X, Y in A. Is it true? Yes. That is symmetric, of course. If X is painted by, X and Y are painted by a certain artist, and of course then Y and X are painted by the same artist, right? Antisymmetric. Okay. If X related with Y and Y related with X, does this mean X and Y are the same? Not necessarily. They could be two different paintings painted by the same artist. Yeah. And it's definitely transitive. If X is painted, X and Y are painted by the same artist, and Y and Z are painted by the same artist, that means X and Z are painted by the same artist. So that means all it is reflexive, not irreflexive, symmetric, and then it was not antisymmetric, and finally it was transitive. So we have these things satisfied: reflexive, symmetric, and transitive. These three properties you will notice that will be satisfied by many of the relations. Okay. And we then therefore name them. A relation is called an equivalence relation if it is reflexive, symmetric, and transitive. Okay. It's from logic that we said a relation is okay. An equivalence equation is equivalent to another equation. So it's very similar. A relation is equivalent to another relation if it is reflexive, symmetric, and transitive. Yeah, that one we will study in detail in the next lecture. That property of equivalence relation, and therein we will also look at other things. Any questions? Anyone? If no questions, I would leave you slightly early then. If the questions, I'm at your service.
Not really related. But could this be used to describe four-dimensional space?
Four-dimensional space?
Yes.
What do you mean by
Like
that?
relations to each other. So, like when you get right into it, how points in space relate to each other on a geometric shape in four dimensions. No?
Geometric. Fourth dimension is a parallel dimension which we can think of.
Yeah.
Okay, it's just imagination. That we
Yeah.
all say that, okay, this is a parallel dimension. Some people say that, okay, take a point, make it a string, swing it, put a punch in it, that will be a fourth dimension. So, come on, this is just a visualization to make a torus in space. But if you're a Doctor Who fan, you would say that that's a parallel dimension.
Okay.
That has nothing to do with it.
I know. I
No,
didn't say. I said it wasn't related. But
it is only. It has nothing to do with it. You're welcome. We'll see you later. See you at 2 o'clock, everyone.